So this topic is a little bit different in terms of materials. So the topic before is all related to the urethra, but this one is about the uh, copper and tungsten joint. So that's the quick outlook about the topic from the background experiments and also the results section. So I'm going to tell the background very quick about the nuclear fusion. Um, and similar as other topics, the structural integrity and materials assessments is quite important for the nuclear fusion joint. In his work, it's mainly about the joint at the divertor and to achieve the thermal transfer efficiency, and also need to maintain the structural integrity of the components. So the joint is made of the copper, chrome, zirconia, and tungsten with the copper as interlayer. Because this is dissimilar joint and is composed of many materials, and so it's quite easy to have residual stress induced into the joint. So I'm going to skip that because we talked about that 3 times. And then is the one of his main techniques for characterizing the residual stress, because that's the dissimilar joints and there are many interlayers, and between the different materials, the region is quite narrow. So for the conventional techniques like neutron diffraction is not very suitable for these materials because the one neutron spot size is about 1.4 millimeter, but actually the interlayer or the interface of these materials can be less than 1 millimeter. So we have to use the high resolution techniques, which is plasma focus ion beam and digital image correlation method. We can remove the restrictions using the plasma focus ion beam to release the residual stress. And after each milling step, we use the SEM to take the images and recording the stress release procedures. And then finally, we use the DIC to analyze the stress release and then achieve the measurement. And here is the basic mechanism about the DIC work. The software or the algorithm check the similarity in this window and then analyze or calculate how the materials deforms during the stress release. Here is the experiments procedures. We do the incremental milling and we take the SEM image and we use the DIC to mark this region and analyze the deformation of this region during the stress release. And after the calculation at each incremental milling, we fit the stress release value at each incremental point, and we finally using this master curve to have the residual stress results, residual strain release results. Because copper and tungsten has relative large grain size, and actually the milling the pillar size is not that huge enough to get the bulk properties. So in this case, we apply the EBSD to measure the grain orientation in this measurement area, and we calculate the anisotropic Young's modulus and the Poisson ratio, and apply that to the Hooke's law to calculate the localized residual stress distribution in the different direction. For the DIC technique, some materials not the natural pattern, natural features of the materials is not very helpful for the DIC analysis because it's too smooth and there is no features to be tracked during the correlation. So we need to generate some artificial features to to help to increase the accuracy of the DSE analysis. So here is like a general three methods about the particle deposition using the FABE, and also the nanoparticle spraying, as well as the last one is the etching. And after etching, is actually use the natural particles of the materials. So each method has its pros and cons. For the etching, it's cheap, fast, but it's not suitable for every materials. And for the deposition, it's kind of universal method, but it's actually really time consuming, and the source is also quite expensive. So we have another option, which is nanoparticle spraying. It can increase the quality of the speckle pattern, and then let's see the results of those three methods. The first one is the original surface without any treatment, and we can see the correlation coefficients of each map. For the rest of the three methods, they almost gave quite similar quality of the correlation, and the nanoparticles slightly win this computation. And then is the plasma focus M beam DSE results of the residual stress. And we can see the residual stress distribution. It has the interface is about 200. Sorry, the interval between two measurements is about 200 micrometers, and we can see the distribution of this line scan. We can find the tensile residual stress as the tungsten copper interface, balanced by the compressive at the two other sides. And also, in his work, he also studied the microstructure effects for the residual stress distribution, because his sample is suffered the high heat flux. So after the thermal history, the recrystallization happens, and the residual stress released in that field. We can find the results here, but the unaffected region still keep the residual stress in the materials. So here is the importance of this method. So in this case, we have like two key importance of this techniques. The firstly, we can measure the residual stress at high resolution. In this case, it's 200 micron, but we can still make the resolution much more higher. So for the materials with complex interface, we can really measure the details of the residual stress distribution. And another thing, we can correlate with the microstructures to find out the localized Young's modulus and Poisson ratio, and find out the real residual stress distribution at the localized space. Here, that's it, and